In this unit, we are going to be talking about exponentials and logarithmic functions. So the only strange type of function we've seen thus far, like back in Unit 2 when we were doing parent functions, was the square root function where the graph looked kind of funky. We also have had the reciprocal or the rational functions that have asymptotes. So exponential and logarithmic functions also have asymptotes due to some restrictions, and they are a funkier looking graph. So in this first section, we are going to be graphing exponentials and logarithmic functions. So first, how do I identify an exponential function? It is going to have the variable up in the exponent. That is what makes it exponential. So 3 to the x, that is an exponential function. Now, what's kind of interesting about exponentials, going back to our parent functions, there is not a solid parent function like there were with other functions. Y equals x squared, parent quadratic. Y equals square root of x, parent square root function. But I could have y equals 5 to the x, y equals 7 to the x, and those would all be separate parent functions depending on the base. So the first thing that is our exponent rules. What's something that's easy to take 3 to the power of? 1's a nice easy input that I can use for x. So 1 is going to be part of our parent table. If I plug in 1, 3 to the first is 3. Now, what is another value that's fairly easy to plug in? 2, which would give us 9, which is kind of off the graph. It's not too bad. 0 is a great one, though, because what's 3 to the 0? 1. Anything to the 0 power is 1. So that's going to come into play a lot, and you can always check it on your calculator. So 3 to the 0, boom, gives us 1. Now the last power, you might argue with me and go, I don't think that's very easy to plug on, Mrs. Cairo, is -1. Contrary to what some of us said on the last test on Friday, 3 to the -1 is not -3. What is it? It's 1 over 3, or 1/3. So when we go to graph these, instead of using transformations like we did back in Unit 2, we're instead going to try to focus on getting our power to be equal to those values. So we're going to call those the power values. Now you'll notice there's a pattern between what we got for our y values and the starting base. This would be 1 over the base. This is always 1. And this is b. So this is kind of our parent table. But again, that's going to vary whether we have base 3, base 5, base 7. So instead of using transformations, we're strictly going to be plugging in inputs for our x to figure out easy outputs. There are 2 types of exponential functions. The first is exponential growth, where our base is greater than 1, and exponential decay, where our base is between 0 and 1, or in a general sense, it's a fraction or a decimal. Now, my favorite example of exponential growth, you guys have probably heard that example of multiplying like rabbits. So you start off with 2 bunnies, then you have 4 bunnies, then you have 8 bunnies, then you have 20 bunnies, then you have 100 bunnies, and then 500 bunnies. And pretty soon you have a lot of bunnies. Instead of it growing in a straight increase, like in a linear fashion, it starts off small and then starts getting larger very, very quickly. So next to exponential growth, I want you to write bunnies. But other things grow exponentially too. Lots of different populations. Bacteria, viruses grow exponentially, unfortunately, as well. So this unit has a lot of real-world applications that we can get into. There's certain types of savings accounts that grow exponentially. Credit card debt can grow exponentially, unfortunately. So there's lots of good applications that will come into play with these exponential functions. Now, exponential decay, my favorite example is caffeine. How many of you have ever had a Red Bull before, or some sort of energy drink? So what happens is you start way up here, woo, energy high. And then what happens? The crash, the major crash where your energy just plummets. So in a general sense, exponential growth gets really, really quickly, really, really large, really, really quickly. And then exponential decay starts off really large and then plummets or crashes. So that's kind of a good reminder for what those graphs will look like. Now, you'll notice that both of these graphs are sort of leveling off, almost as if they have some sort of asymptote that they are approaching on the bottom. So, folks, I want you to consider this. If I plugged 0 in for y, is there anything I can plug in for x to give me an output of 0? No, because I could plug in 0, but that gives me 1. And as I keep plugging in negatives, I'm going to get smaller and smaller fractions. As I keep plugging in positive numbers, we're going to get larger and larger and larger. So there's no way for me to get a value of 0. Here's the other kicker. Try plugging in -3 for y. Can I take +3 to an exponent and get a negative? Nope, we cannot. So because of our restrictions on how the function behaves, there is a horizontal asymptote at y equals 0. Because we're not going to be able to get a y value of 0 or go anywhere below it to get negative values. Now, your horizontal asymptote will move if there are up-down transformations. So we are going to go back in time to first term a little bit to review our transformation rules. If you're like, ugh, thought we were done with those, Ms. Cairo. Those of you going on to finite transformation rules come back into play. Those of you going on to trig transformation rules come back into play. Those of you taking the ACT in the spring, transformation rules is a nice thing to refresh in this unit. So logarithmic functions, we're not going to do anything with those quite yet, but we will start exploring them today and a lot more later on in this unit. So logarithmic functions we'll talk about later. So asymptote, an imaginary line that the graph approaches, and exponential graphs have horizontal asymptotes. So we're going to graph the following exponential functions and state the domain and the range. Domain is the x values that get covered by the graph, and the range is the y values. So we're going to start by looking at this equation. How do I know that that's an exponential function? It's got a variable in the exponent. Boom. That is what makes it exponential. So just like x squared makes something a quadratic, having an exponent of x is what makes it an exponential function. Looking at the base, is this a growth or a decay function? It's growth. Our base is greater than 1, so this is growth. Are there any transformations happening with this problem? If you look at that and go, is that 3 like a vertical stretch, or does it move it left or right? 3 is just the base. It does not do anything. So just put a note that says no transformations, which means our horizontal asymptote is going to be right at 0. Horizontal asymptote at 0. And we're going to go ahead and draw that in. So a dashed line. At y equals 0. So just like the asymptotes were a big part of our rational graphs, the asymptotes are going to be a big part of our exponential and logarithmic graphs as well. Now, for our points, if you're like, I'd sure like to just grab my calculator and type it in and go to the grapher and see what it looks like, you can certainly use your grapher to check yourself, but I am going to be looking for table work on all of these on the homework. And the only thing I need to see are 3 easy points. What we want to do is choose values that make our exponent -1, 0, and 1. Now, since there are no transformations here, we can just straight up plug in -1, 0, and 1 in for x to get our corresponding y values. So what's 3 to the -1? 1 over 3 or 1/3. 3 to the 0 is 1. And 3 to the first is 3. Let's go ahead and plot our points. Backwards 1, up 1/3, super close to the asymptote. And then 0, 1, and 1, 1, 2, 3. And if you wanted to plug in an extra point and say plugging in 2 would give me 9, you could do that as well. And that just shows you that we start getting larger very, very quickly. So we're going to curve up through those points, putting an arrow on that end. And then remember what we've said about asymptotes before. It's like that younger sibling that goes, I'm not touching you, I'm not touching you, but they're literally like right in your face. That's what this graph is going to do to the asymptote. I'm not touching you, I'm not touching you, but it is getting very awkwardly close. So we do need arrows on both sides of the graph, and that is our exponential growth function. Now for our domain. What x values are going to get covered by this graph? It's going to go all the way left, and it's going to keep going upward and outward to the right. What do you think? All real numbers, or the fancy R. Or, if you would like to do interval notation, which I do recommend for you future pre-calcers, -infinity to +infinity. You can also think about it from an algebraic standpoint. What can I plug in for x? Literally anything. But for our outputs or our range value, we know that we're going to have some restrictions. Is my graph ever going to get down into those negative values? No. What is the first value that we start with? Our y values start up just slightly above that asymptote. How we are going to express that using inequality notation is y greater than 0. That means 0 itself, or the asymptote value, isn't included, but anything slightly above it would be included as part of our range. So this is the first time we've ever used greater than instead of greater than or equal to. With interval notation, you would do parentheses 0 to infinity. Whereas before, when we dealt with absolute value graphs and square root functions, we always had the bracket. So to show that the asymptote is not included, you would use greater than or a parenthesis. So there's kind of a lot to unpack here. First, we look at the equation and determine if there are any transformations to find the asymptote first. Next, we make our table, trying to get our powers to be equal to those easy values. Plot the points, make your curve, and then read what x values and y values get covered by the graph. Does anybody have any specific questions so far? Other than gross, we're back into graphing. And folks, just as a reminder, if you wanted to check yourself on your calculator, you could type in 3 to the x. I don't know why that's off center, zoom standard. And we would see that that's what our graph should look like. So you can check yourself this way, but I am still going to be looking for the table work and stating the transformations. So let's go ahead and look at this next one. First, transformation-wise, what is that +1 on the outside doing to our function? Up 1. So remember, outside transformations, we think of our arm. Positives go up, negatives go down. What about inside transformations? What do positives do? to the left, and then negatives will go to the right. So we'll be refreshing all of these as we work through these problems. So this goes up 1. What is that negative getting multiplied out in front do? Vertical reflection. What does the 2 do? Psych, trick question. The 2 doesn't do anything transformation-wise. It is simply the base. But it does tell us that this is a growth function. So this one does have transformations. So to figure out where my asymptote is going to be, we are going to transform that parent key feature visually. So my asymptote starts at 0. I should probably do this on the screen so folks don't see. So we start with our asymptote at 0. So a horizontal line going through 0. If I vertically reflect that, has it moved? Nope, it's still in that same spot at 0. So vertical reflection doesn't move it. But if I slide it up 1, are we in a new location? Yes, the up 1 is going to move our asymptote up 1 unit to be at y equals 1. So this is what I meant by the up-down transformations will move that horizontal asymptote that starts at y equals 0. Any questions on the transformation so far, that first step? So we state the transformations, we visually move the asymptote. Let's go ahead and write these steps down. So step 1, state the transformations, and then growth or decay. Number 2, use the transformations to move the asymptote, which starts at y equals 0. Our next step is going to be make our table using the power values. Which will be the -1, 0, and 1. So we look at our power. It is just x. So in order for me to get our power to be equal to -1, 0, and 1, I can simply plug in those values for x. So -1, 0, and 1. Now for the tricky part, your favorite acronym that continues to haunt us, PEMDAS. If I plug in -1, am I going to take -2 to the -1 or 2 to the -1 and then the opposite of it? We handled the exponent first. So let's not do the -1 first. Let's go ahead and do +1. What's 2 to the first? 2. The opposite of 2 is -2, and then +1 is -1. Exponent, opposite sign, add the 1. Now we'll plug in 0. What's 2 to the 0? 1. The opposite of that, -1. And -1 plus 1 is 0. We plug in -1. 2 to the -1 is 1/2. The opposite of that is a -1/2. What's -1/2 plus 1? 1/2. If you are getting stuck with some of those powers or those fractions, you can certainly use your calculator to help you. And now we plot our points. So backwards 1, up 1/2, 0, 0, 1, -1. So we are getting exponentially larger going this way. And then we're sneaking, getting closer and closer towards the asymptote. Arrows on both sides. And if you're like, wait, how is that exponential growth if it's like going down? Yeah, the reason it's going down is because it's been vertically reflected. But can we have negative values that grow exponentially? Student loan debt, woo! So you can go in debt exponentially or grow in the opposite direction. So this is still a growth function, which is why we always use our definition of what the base is, not necessarily how the graph looks. So folks, the domain for this one, what do you think? What x values are going to get covered by my graph if we go all the way left and that arrow keeps on going to the right? It's all real numbers. Spoiler alert, it's actually going to be all real numbers for all exponentials. So we can actually choose that as a key feature by our horizontal asymptote. The domain is always all real numbers. Now the range is going to depend on the location of the asymptote. So if you want to use inequality notation, how do we say that our y values are covered for anything below the asymptote at 1? Y is less than 1. Y is less than 1. Now if you want to use interval notation, interval notation has to go in sequential order, so you have to start at negative infinity and stop at 1 with a parenthesis. So it has to be this, not 1 negative infinity. So that is not okay. So you can use either notation, just like we said in the past, but if you want to use interval notation, make sure you read it from the bottom up, from negative infinity to infinity. How are we doing? Oof, Monday. Here's what we're going to do. I think we'll go through one more example, and then I think we'll go over your test before lunch. So let's go ahead and look at our next one. We've got y equals 1/3 to the x. So is this an exponential function? Yup, it's got x in the exponent. Are there any transformations? We've got the 1/3, which is just the base. What does that tell me? Is this growth or decay? This is going to be our first decay function. Where is decay? So if there are no transformations, where is our horizontal asymptote going to be? Where does that key feature start? 0. So y equals 0. So there's our first 2 steps. State the transformations, growth or decay. Use transformations to move the asymptote. Hooray. Next, we want to make our table. And we want to make our power, or our exponent, be equal to -1, 0, and 1. There's nothing up with the x, so I can just straight up plug in those values. It's a little bit different because we have a fraction, but the values are all fairly nice. See if you can find the corresponding outputs for this one. You can use your calculator to help you if you need to, but we should be able to do this by hand. What happens when we give that -1 a bad attitude and send it downstairs, and then 3 a bad attitude and send it upstairs? What do we get? 3/1 or just 3? What's 1/3 to the 0 power? Anything to the 0 power is 1. What's 1/3 to the first? 1/3. So yeah, there are fractions involved, but it's fairly light at this point. So backwards 1, up 3, 0, 1, 1, 1/3. So do you think it's leveling off towards the asymptote on the right side or the left side? on the right side, so closer, 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 closer. Arrow going this way, and swoosh, exponentially larger going up. We have a Red Bull, and we crash exponentially. My graph's a little pointy. It should be curved. There we go. I'm going to turn you loose on the domain and range using interval notation or inequality notation. You do not have to do both. See if you can state the domain and range for this one. Domain, all real numbers, negative infinity to positive infinity. The range, y is greater than 0. 0 is not included. We don't actually ever touch that asymptote, but anything slightly above it is going to work. So 0 to infinity or y greater than 0. How did we do? Just kidding. We're going to do this last problem too, and then we'll look at your test. What's different about this problem? It's x plus 2, so our exponent has more stuff with it, which is what's going to change my power. Well, the power values stay the same, but how we use them is going to be a little bit different. So let's go through our steps again. First, state the transformations. So what's that 2 out in front doing to our function? Vertical stretch by 2. What's that 1/3 doing? How do I know that the 1/3 is the base and not the 2? Because of the exponent. So the 1/3 is what has the exponent. The base corresponds to what's tied to the exponent. So our base is 1/3. That's a decay function. Okay, now here's the tough one. We've got a plus 2 on the inside with x. Those inside ones, we cross our eyes, and they do the opposite of what we would think for that sign. So a plus 2 is going to move us left 2. And what about that minus 3 on the outside? Down 3. So state the transformations, done. Growth or decay, done. Now we're going to use the transformations to move the asymptote. My asymptote starts at 0. If I vertically stretch it or pull on it, it doesn't do anything. It stays in that same spot. The base does nothing. If I move a horizontal line left 2, is that horizontal line actually moving? No, it's still at y equals 0. But if I slide it down 3, has it moved? Yes. So we used our transformations to visually move the asymptote, and that down 3 is the only one that affects it. So now our asymptote is at y equals negative 3. So step 2 is done. Next, our table using the power values. Now, let's just say I want to type in 1. If I plug in 1 for x, I get 1 plus 2 is 3. Do I want to take 1/3 to the 3rd power and then multiply that by 2 and subtract 3? Not really. Anything larger than 1 is unfriendly. Anything smaller than -1 starts to get really gross with fractions as well. So for this problem, I can't just straight up plug in -1, 0, and 1 because we need to get our exponent to be equal to those values. So to the side of your table, I want you to write -1, 0, and 1, and write we want to get our power to be these values. By choosing different x values. Now, I normally don't like to start with the negative, I normally start with the positive and say, what could I plug in for x so that my whole exponent, x plus 2, would be equal to positive 1? What could I plug in for x so that x plus 2 is 1? Negative 1. So if I plug in negative 1 for x, I'm going to get that nice power value. What could I plug in for x to make my whole exponent be equal to 0? Negative 2. Because negative 2 plus 2 makes the whole exponent 0. So what could I plug in for x to make my exponent negative 1? Negative 3. And now we use PEMDAS. So I first plug in negative 3. Negative 3 plus 2 is negative 1. What's 1/3 to the negative 1? What happens when I give that fraction a bad attitude? We flip it and it turns into 3. 3 times 2 is 6. And 6 minus 3 is 3. Let's do that again. We take the x input and plug it in. Negative 3 plus 2 is negative 1. 1/3 to the negative 1. It flips the whole fraction, gives it a bad attitude, and flips it to be 3. Then we multiply. 2 times 3 is 6. And that 6 minus 3 is 3. Try the next one on your own. What happens when we plug negative 2 in for x following PEMDAS? So negative 2 plus 2 is 0. What's 1/3 of the 0 power? 1. 1 times 2 is 2. And 2 minus 3 is negative 1. Raise your hand if you got that one right. Good, we're working on it. Plugging in negative 1. Negative 1 plus 2 is 1. 1/3 to the first power is 1/3. 2 times 1/3 is 2/3. Now, folks, if I have 2/3 minus 3, sometimes I like to think of this in terms of mixed numbers. So if I have 2/3 of a pizza and I subtract 3, I'm going to be in debt negative 2 1/3 pizzas. You could also use your calculator on this. Or you could find common denominators, which is even better. But if you wanted to do it quickly, 2 divided by 3 minus 3, we can see is negative 2.3 repeating, or negative 2 1/3. And a lot of times I like to write it as a mixed number versus an improper fraction because it's a little bit easier for graphing. Now, when we go to graph these, make sure you graph these points as your XY pairs and not those ones. The negative 1, 0, and 1 is not the start of our coordinate here. That's just what we were trying to get our power values to be equal to so that it was easier to plug in. So let's go ahead and plot those points. Negative 3, 3. Negative 2, 1. Negative 1, negative 2 1/3, so just a titch more. What side do you think we're leveling off towards the asymptote on? Whoop, that should be negative 2, negative 1. My bad. I thought that looked a little funny. Ignore this point. Are we leveling off towards the asymptote on the right or on the left? It looks like we're heading down this way and then heading upward. On your own, the domain and the range. I greater than -3. -3 to infinity. All right, folks, so that is graphing exponentials. We're going to do some more practice with that after lunch. In the meantime, if you have not taken the test, please skedaddle out in the hallway. Everyone else, phones on the floor while I pass these out.
I go to the bathroom.
Yes.